Solutions are homogeneous mixtures made up of two or more components, characterized by a uniform composition and consistent properties throughout the mixture. In these solutions, the component present in the largest quantity is known as the solvent. The solvent is crucial as it determines the physical state of the solution, whether it is a liquid, gas, or solid. The other components, which are not the solvent, are referred to as solutes. This discussion will specifically focus on binary solutions, which consist of exactly two components. The composition of a solution can be described using concentration, which can be expressed in both qualitative and quantitative terms. Qualitative descriptions, such as labeling a solution as dilute or concentrated, can sometimes lead to ambiguity. Therefore, a quantitative description is essential for clarity and precision in scientific contexts. Several methods exist for quantitatively describing the concentration of a solution, each with specific applications and significance. The first method is mass percentage, WW. This is defined as the mass of a component in the solution divided by the total mass of the solution, multiplied by 100. For example, if a solution is described as containing 10% glucose by mass, it indicates that there are 10 grams of glucose dissolved in 90 grams of water, resulting in a total solution mass of 100 grams. This method is commonly used in industrial chemical applications. For instance, a commercial bleaching solution contains a mass percentage of 3.62% sodium hypochlorite in water, indicating the precise amount of active ingredient present. The second method is volume percentage, VEV, which measures the volume of a component divided by the total volume of the solution multiplied by 100. For example, a 10% ethanol solution in water means that 10 molecules of ethanol is dissolved in water to achieve a total solution volume of 100 ml. This unit is particularly useful for solutions containing liquids. A practical example is a 35% VV solution of ethylene glycol, commonly used as an antifreeze in automobiles. At this concentration, the antifreeze effectively lowers the freezing point of water to 255.4 K, 17.6 which is essential for engine cooling in cold conditions. Another important unit is mass by volume percentage, V, which is frequently used in medicine and pharmacy. This unit is defined as the mass of solute dissolved in 100 mL of the solution. For example, a saline solution might be described as having a concentration of 0.9% V sodium chloride, indicating that 0.9 grams of sodium chloride is dissolved in 100 mL of the solution. This measurement is critical for preparing intravenous fluids and other medical solutions. When solutes are present in trace quantities, it is convenient to express concentration in parts per million, ppm. This is defined as the number of parts of the component divided by the total number of parts of all components in the solution multiplied by 1 million. For instance, a liter of seawater, which weighs approximately 1030 grams, contains about 610 to the power of 3 grams of dissolved oxygen. This small concentration can also be expressed as 5.8 grams per 10 to the power of 6 grams of seawater, or 5.8 cm. This unit is particularly useful for measuring pollutants in water or air, where concentrations can be extremely low. Mole fraction is another significant measure, commonly represented by the symbol X. The mole fraction of a component is defined as the number of moles of that component divided by the total number of moles of all components in the solution. In a binary mixture, If component A has Na moles and component B has Nb moles, the mole fraction of A can be calculated using the formula XeA plus Nb. This unit is valuable for relating physical properties, such as vapor pressure, to the concentration of the solution. It also plays a significant role in calculations involving gas mixtures, where understanding the proportion of each gas is critical. Molarity, M, is another widely used concentration unit, defined as the number of moles of solute dissolved in 1 liter or 1 cubic decimeter of solution. For example, a 0.25 mol L to the power of 1 or 0.25 yam solution of sodium hydroxide means that 0.25 moles of NaOH have been dissolved in 1 liter of solution. Molarity is frequently used in laboratory settings for preparing solutions and conducting experiments. Lastly, molality, M, is defined as the number of moles of solute per kilogram of solvent. It is expressed as molality, M equals moles of solute, mass of solvent in Ke. For example, a 100 mole Kg to the power of 1 or 1 term solution of potassium chloride means that 1 mole, 74.5 grams, of Kc is dissolved in 1 kilograms of water. Molality is particularly useful in scenarios where temperature changes may affect volume, as it remains independent of temperature. Each method of expressing the concentration of solutions has its own merits and demerits. Mass percentage, ppm, mole fraction, and molality are independent of temperature, while molarity is affected by temperature changes due to its reliance on volume. Understanding these various measures is crucial for accurately characterizing solutions and ensuring proper application in scientific and industrial contexts. Solubility is a crucial concept in chemistry, defining the maximum amount of a substance that can dissolve in a specified amount of solvent at a specific temperature. This property is influenced by the nature of both the solute and solvent, as well as external conditions such as temperature and pressure. Understanding solubility is essential for various applications, from industrial processes to biological systems. When examining the solubility of solids in liquids, it is important to note that not all solids dissolve in every liquid. For example, sodium chloride and sugar dissolve readily in water, making them common examples of soluble substances. In contrast, compounds like naphthalene and anthracene do not dissolve in water. Interestingly, these non-polar solids dissolve well in non-polar solvents like benzene, while polar solutes such as sodium chloride and sugar remain insoluble in benzene. This behavior illustrates the principle of like dissolves like, where polar solutes typically dissolve in polar solvents and non-polar solutes dissolve in non-polar solvents. The process of dissolution begins when a solid solute is introduced into a solvent. Initially, some solute particles dissolve, increasing their concentration in the solution. This process is referred to as dissolution. However, as solute particles enter the solution, they can also collide with solid solute particles, leading to a process known as crystallization. Over time, a dynamic equilibrium is established when the rates of dissolution and crystallization become equal. At this equilibrium stage, the concentration of solute remains constant under specific conditions, such as temperature and pressure. It is essential to differentiate between saturated and unsaturated solutions when discussing solubility. A saturated solution is one in which no more solute can dissolve at the current temperature and pressure, meaning it contains the maximum amount of solute that can be dissolved in a given volume of solvent. Conversely, an unsaturated solution can still dissolve additional solute, indicating that it has not yet reached its solubility limit. Temperature significantly influences the solubility of solids in liquids. Generally, if the dissolution process is endothermic, meaning it absorbs heat, delta Sol H0, increasing the temperature will enhance solubility. Conversely, if the dissolution process is exothermic, delta Sol H0, raising the temperature will decrease solubility. These trends have been observed in various experimental settings, highlighting the importance of temperature in solubility dynamics. In contrast, pressure has a minimal effect on the solubility of solids in liquids. This is primarily because both solids and liquids are highly incompressible, meaning they remain largely unaffected by changes in pressure. However, gases exhibit different behavior regarding solubility in liquids. Many gases can dissolve in water, but the extent of their solubility varies widely. For example, oxygen dissolves only to a small extent in water, yet this dissolved oxygen is vital for sustaining aquatic life. In contrast, gases like hydrogen chloride, HCl, are highly soluble in water. The solubility of gases in liquids is significantly influenced by both pressure and temperature. According to Henry's law, at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of that gas above the liquid surface. This relationship can be expressed mathematically as P equal kH multiplied by X, where P represents the partial pressure of the gas, X is the mole fraction of the gas in the solution, and KAH is the Henry's law constant. Different gases have unique KAH values at the same temperature, indicating that solubility is specific to the nature of the gas. A higher KAH value corresponds to lower solubility in the liquid. For example, KAH values for gases like nitrogen and oxygen tend to increase with rising temperature, suggesting that gas solubility decreases as temperature increases. This is particularly relevant for aquatic species, as they thrive in cooler waters where oxygen solubility is higher. Henry's law has numerous practical applications in various industries and biological contexts. One notable example is the carbonation of soft drinks. To increase the solubility of carbon dioxide in beverages, bottles are sealed under high pressure, allowing more gas to dissolve in the liquid. This process creates the fizzy sensation that many consumers enjoy. Scuba divers also encounter challenges related to gas solubility. When diving, they breathe air at high pressures, which increases the solubility of atmospheric gases in their blood. As divers ascend, the pressure decreases, leading to the release of dissolved gases and potentially forming nitrogen bubbles in the blood. This condition, known as the bends, can be extremely painful and even life-threatening. To mitigate this risk, divers often use gas mixtures that include helium, which reduces the likelihood of nitrogen bubbles forming during ascent. Furthermore, at high altitudes, the partial pressure of oxygen is significantly lower than at sea level. This reduction leads to decreased oxygen concentrations in the blood and tissues of individuals living at high altitudes or climbers. The resulting low blood oxygen levels can cause weakness and impaired cognitive function, symptoms associated with a condition known as anoxia. Temperature plays a crucial role in determining the solubility of gases in liquids. As the temperature of a liquid increases, the solubility of gases within that liquid decreases. This phenomenon occurs because when a gas dissolves in a liquid, it releases heat, a process that can be likened to condensation. The dissolution of gas molecules into a liquid phase is an exothermic reaction, meaning heat is released during the process. This release of heat leads to a dynamic equilibrium that must adhere to Le Chatelier's principle, which states that a system at equilibrium will adjust to counteract any changes imposed on it. Consequently, as the temperature rises, the solubility of gases decreases as the system seeks to counterbalance the added thermal energy. Liquid solutions are formed when a liquid solvent interacts with a solute, which can be a gas, liquid, or solid. The nature of the solute significantly influences the properties of the solution. In many cases, the solvent is volatile, meaning it can easily evaporate, while the solute may or may not possess volatility. This distinction is essential for understanding how different types of solutions behave under varying conditions. When considering a binary solution composed of two volatile liquids, both components will evaporate when contained in a closed vessel. Over time, an equilibrium is established between the vapor phase and the liquid phase. At this equilibrium stage, the total vapor pressure, denoted as P total, is the sum of the partial pressures of the two components, P per 1 and P per 2. The relationship between these pressures and their corresponding mole fractions is described by Raoult's law, a principle formulated by the French chemist François-Marc Raoult in 1886. Raoult's law provides a quantitative relationship, stating that the partial vapor pressure of each component in a solution is directly proportional to its mole fraction. For component 1, this relationship can be expressed mathematically as P1 proportional to X1, where P1 to the power of 0 represents the vapor pressure of pure component 1 at the same temperature. A similar expression applies for component 2, establishing a clear connection between the mole fractions and the partial pressures of the components. According to Dalton's law of partial pressures, the total pressure over the solution, P total, can be calculated as the sum of the partial pressures of the individual components, leading to the equation P total equals P1 plus P2. Several key conclusions can be drawn from this analysis. 1. The total vapor pressure over the solution can be related to the mole fraction of any one component. 2. The total vapor pressure over the solution varies linearly with the mole fraction of component 2. 3. Depending on the vapor pressures of the pure components 1 and 2, the total vapor pressure over the solution may either increase or decrease with an increase in the mole fraction of component 1. When plotting P1 or PT2 against the mole fractions X1 and X2, a linear graph emerges, illustrating the direct relationship between the partial pressures and mole fractions. The composition of the vapor phase in equilibrium with the solution is determined by the partial pressures of the components, further emphasizing the interconnectedness of these principles. Raoult's law can also be understood as a special case of Henry's law. According to Raoult's law, the vapor pressure of a volatile component in a solution is given by the equation P1 EGI extron 1 multiplied by P1 to the power of 0 in the context of a gas dissolved in a liquid. Henry's law describes the solubility of the gas as P equals KH multiplied by X, where KH is the Henry's law constant. By comparing the equations for Raoult's law and Henry's law, it becomes evident that the partial pressure of the volatile component or gas is directly proportional to its mole fraction in the solution. The only difference lies in the proportionality constant, KH, which varies from P1 to the power of 0. Thus, Raoult's law is a specific instance of Henry's law, where KH is equivalent to P sart 1 to the power of 0. Another significant category of solutions involves solids dissolved in liquids. Examples include sodium chloride, glucose, urea, and cane sugar in water, as well as iodine and sulfur dissolved in carbon disulfide. The physical properties of these solutions often differ markedly from those of pure solvents. One notable difference is in vapor pressure. At a given temperature, liquids vaporize, and the pressure exerted by the vapor over the liquid phase is termed vapor pressure. In a pure liquid, the entire surface is occupied by liquid molecules. However, when a non-volatile solute is added to a solvent, the vapor pressure of the resulting solution is determined solely by the solvent. This vapor pressure is invariably lower than that of the pure solvent at the same temperature. The reduction in vapor pressure can be attributed to the presence of both solute and solvent molecules at the surface. Consequently, the fraction of the surface occupied by solvent molecules decreases, leading to a corresponding reduction in the number of solvent molecules that can escape into the vapor phase. The extent of this decrease in vapor pressure depends on the quantity of non-volatile solute present in the solution, regardless of the solute's nature. For instance, adding 1.0 mole of sucrose to 1 kg of water produces a decrease in vapor pressure, similar to that caused by adding 1.0 mole of urea to the same quantity of water at the same temperature. In its general form, Raoult's law states that for any solution, the partial vapor pressure of each volatile component is directly proportional to its mole fraction. Liquid-liquid solutions can be categorized into two primary types: ideal and non-ideal solutions, based on the principles of Raoult's law. This classification is essential for understanding how different solutions behave under various conditions. Ideal solutions are defined as those that adhere to Raoult's law throughout the entire range of concentrations. These solutions exhibit two key properties. The enthalpy of mixing is 0, and the volume of mixing is also 0. A 0 enthalpy of mixing indicates that no heat is absorbed or released during the mixing process, making it energetically neutral. Additionally, a 0 volume of mixing means that the total volume of the solution is equal to the sum of the individual volumes of the pure components. This characteristic simplifies calculations in various chemical processes. At the molecular level, ideal behavior occurs when the intermolecular forces between like molecules, A and B, are nearly equal to the forces between unlike molecules, AB. When these interactions are balanced, the solution behaves ideally. Although perfectly ideal solutions are rare, several mixtures exhibit behavior that closely approximates ideality. Examples include N-hexane with N-heptane, bromoethane with chloroethane, and benzene with toluene. These mixtures demonstrate properties that align closely with the predictions of Raoult's law. In contrast, non-ideal solutions do not follow Raoult's law across all concentrations. The vapor pressure of such solutions may be either higher or lower than predicted. When the vapor pressure is higher than expected, the solution exhibits positive deviation from Raoult's law. This occurs when the interactions between solute and solvent molecules, AB, are weaker than the interactions among solute-solute, AA, and solvent-solvent, BB, molecules. In cases of positive deviation, molecules of A or B find it easier to escape into the vapor phase compared to their pure states, resulting in an increased vapor pressure. A classic example of positive deviation is the mixture of ethanol and acetone. In pure ethanol, strong hydrogen bonds hold the molecules together. However, when acetone is added, its molecules disrupt these hydrogen bonds, weakening the interactions and allowing more ethanol molecules to escape into the vapor phase, thereby increasing the vapor pressure. Another example of positive deviation can be observed in the mixture of carbon disulfide and acetone. In this scenario, the dipolar interactions between solute-solvent molecules are weaker than the interactions among solute-solute and solvent-solvent molecules, leading to a similar increase in vapor pressure. Negative deviation from Raoult's law occurs when the intermolecular attractive forces between the pure components, AA and BB, are weaker than the interactions between the mixed components, AB. This results in a decrease in vapor pressure. An example of negative deviation is found in a mixture of phenol and aniline. In this case, the intermolecular hydrogen bonding between the phenolic proton and the lone pair on the nitrogen atom of aniline is stronger than the respective hydrogen bonding among similar molecules. This stronger interaction reduces the escaping tendency of the molecules, resulting in a lower vapor pressure. Similarly, a mixture of chloroform and acetone forms a solution that exhibits negative deviation from Raoult's law. The ability of chloroform molecules to form hydrogen bonds with acetone molecules decreases the escaping tendency of the molecules, leading to a lower vapor pressure. Additionally, certain liquid mixtures form azeotropes, which are binary mixtures characterized by having the same composition in both the liquid and vapor phases and boiling at a constant temperature. Azeotropes present unique challenges in separation processes, as it becomes impossible to separate the components by fractional distillation. There are two primary types of azeotropes: minimum boiling azeotropes and maximum boiling azeotropes. Solutions that exhibit significant positive deviation from Raoult's law tend to form minimum boiling azeotropes at specific compositions. A well-known example is the ethanol-water mixture, commonly obtained through the fermentation of sugars. During fractional distillation, this mixture reaches a composition of approximately 95% ethanol. At this azeotropic composition, the liquid and vapor phases have the same composition, preventing further separation. Conversely, solutions that demonstrate substantial negative deviation from Raoult's law form maximum boiling azeotropes at specific compositions. An example of this class of azeotrope is the mixture of nitric acid and water, which has an approximate composition of 68% nitric acid and 32% water by mass, with a boiling point of 393.5 K. Understanding these classifications and properties is crucial for various applications in chemistry and industry. They influence processes ranging from distillation to the formulation of solutions in pharmaceuticals and chemical manufacturing. Furthermore, the study of colligative properties, which depend on the number of solute particles rather than their identity, is critical for understanding solution behavior. These properties include relative lowering of vapor pressure, freezing point depression, boiling point elevation, and osmotic pressure. Relative lowering of vapor pressure indicates that the vapor pressure of a solvent in a solution is lower than that of the pure solvent. Raoult established that this lowering depends solely on the concentration of solute particles, regardless of their identity. In solutions containing multiple non-volatile solutes, the overall lowering of vapor pressure is determined by the sum of the mole fractions of all solutes present. This comprehensive understanding of ideal and non-ideal solutions, along with their associated properties, is vital for chemists and engineers engaged in the study and application of liquid mixtures in various scientific and industrial contexts. The boiling point of a liquid is a fascinating phenomenon that is influenced by temperature and vapor pressure. As the temperature of a liquid increases, its vapor pressure also rises. This relationship is crucial because a liquid boils when its vapor pressure equals the atmospheric pressure surrounding it. For instance, water boils at 373.15 K or 100 degrees Celsius because at this temperature, its vapor pressure reaches 113 bar, which is equivalent to 1 atmosphere of pressure. However, when a non-volatile solute, such as sucrose, is dissolved in water, the situation changes significantly. The presence of this solute decreases the vapor pressure of the solution compared to that of pure water. At 373.15 K, the vapor pressure of an aqueous sucrose solution is lower than 1.013 bar. Consequently, to make this solution boil, its vapor pressure must be increased to match 1.013 bar. This can only be achieved by raising the temperature above the boiling point of pure water. Thus, the boiling point of a solution is always higher than that of the pure solvent from which it is made. This phenomenon is known as the elevation of boiling point. The elevation of boiling point is not dependent on the type of solute, but rather on the number of solute molecules present in the solution. Experiments have shown that for dilute solutions, the elevation of boiling point, often denoted as dTB, is directly proportional to the molar concentration of the solute. This means that as more solute is added, the boiling point continues to rise. This principle is essential in various applications, including cooking, where adding salt to water raises its boiling point, allowing food to cook more effectively. In addition to the elevation of boiling point, another important concept in physical chemistry is the depression of freezing point. Similar to how the addition of a solute raises the boiling point, it also lowers the freezing point of a solution compared to that of the pure solvent. The freezing point of a substance can be defined as the temperature at which the vapor pressure of the liquid phase equals that of the solid phase. When a non-volatile solute is added to a solvent, the vapor pressure of the solution decreases. As a result, the solution will freeze at a lower temperature than the pure solvent. According to Raoult's law, the addition of a non-volatile solid to a solvent lowers its vapor pressure, causing the freezing point to drop. This depression of freezing point is also directly proportional to the molality of the solution, similar to the elevation of boiling point. The proportionality constant, known as the freezing point depression constant, or KF, varies depending on the nature of the solvent. This constant is measured in units of kg1 mol1 and plays a crucial role in determining how much the freezing point will decrease based on the concentration of the solute. Another intriguing phenomenon related to solutions is osmosis and osmotic pressure. Osmosis is commonly observed in everyday life, such as when wilted flowers revive after being placed in fresh water or when blood cells collapse in saline water. The common factor in these scenarios is the presence of semi-permeable membranes. These membranes can be made from animal or vegetable sources, such as pig's bladder or parchment, or they can be synthetic, like cellophane. Although these membranes appear to be continuous sheets, they contain a network of tiny holes or pores that allow small solvent molecules, like water, to pass through while blocking larger solute molecules. When a semi-permeable membrane is placed between pure solvent and a solution, the solvent molecules will naturally flow from the side with pure solvent to the side with the solution. This process is known as osmosis, and continues until equilibrium is reached, meaning the concentration of solvent is equal on both sides of the membrane. However, if external pressure is applied to the solution, it can stop this flow of solvent. The pressure required to halt osmosis is referred to as osmotic pressure. Osmotic pressure is a colligative property, meaning it depends on the number of solute molecules present rather than their specific identity. For dilute solutions, osmotic pressure has been experimentally found to be proportional to the molarity of the solution at a given temperature. This relationship allows for the measurement of osmotic pressure to serve as a method for determining the molar masses of solutes, particularly useful for proteins, polymers, and other macromolecules. The osmotic pressure method has several advantages over other techniques. It operates at room temperature, making it suitable for substances that may not be stable at higher temperatures. Additionally, it uses molarity instead of molality, which simplifies calculations. The magnitude of osmotic pressure is significant even for very dilute solutions, making it a powerful tool in various scientific fields. In biological contexts, two solutions with the same osmotic pressure at a given temperature are termed isotonic solutions. When separated by a semi-permeable membrane, no osmosis occurs between them. For example, the osmotic pressure inside blood cells is equivalent to that of a 0.9% sodium chloride solution known as normal saline, which is safe for intravenous injection. Conversely, if cells are placed in a hypertonic solution with more than 0.9% sodium chloride, water will flow out of the cells, causing them to shrink. In contrast, a hypertonic solution with less than 0.9% sodium chloride will lead to water flowing into the cells, causing them to swell. In the fascinating world of osmosis, wilted flowers spring back to life when placed in fresh water. This revival occurs as water enters their cells, restoring firmness and vitality. The process of osmosis is essential for many living organisms, as it regulates the movement of water in and out of cells. Similarly, limp carrots regain their crunch through the same process. When placed in water, these vegetables absorb moisture, making them crisp and appealing once again. Osmosis is not just limited to plants. It plays a crucial role in human physiology as well. For instance, when blood cells are placed in a solution with less than 0.9% salt, they swell as water flows into them, demonstrating osmosis in action. This phenomenon is vital for maintaining cellular health. However, excessive salt intake can lead to water retention, causing puffiness known as edema. This swelling occurs as water moves into tissue cells and intercellular spaces, leading to discomfort and health issues. In the plant kingdom, osmosis is a driving force behind water movement from soil into roots and up through the plant. This process is essential for nutrient transport and overall plant health. Without osmosis, plants would struggle to thrive as they rely on this mechanism to absorb water and minerals from the soil. The preservation of food also utilizes the principles of osmosis. Salting meat or adding sugar to fruits protects against bacterial growth by causing bacteria to lose water and shrivel, ultimately leading to their death. This method of preservation has been used for centuries to extend the shelf life of perishable items. Reverse osmosis is a remarkable process that allows for the purification of water. In this technique, pressure greater than osmotic pressure is applied, enabling pure solvent to flow out of a solution through a semi-permeable membrane. This method is particularly significant for desalinating seawater, transforming it into fresh water suitable for drinking and irrigation. The application of reverse osmosis has become increasingly important as global water scarcity issues arise. In reverse osmosis, high-pressure forces pure water out of seawater through membranes made from materials like cellulose acetate. This film is permeable to water but blocks impurities and ions, making it effective for water purification. The technology has advanced significantly, with many countries now relying on desalination plants to meet their drinking water requirements. These plants are crucial in arid regions where freshwater resources are limited, providing a sustainable solution to water shortages. Understanding abnormal molar masses is essential in chemistry, particularly in the study of solutions. When ionic compounds dissolve in water, they dissociate into cations and anions. For instance, dissolving 1 mole of KCl releases 1 mole of K positive and 1 mole of Cl negative ions, resulting in 2 moles of particles in solution. This dissociation affects the properties of the solution, including its boiling point. When 1 mole of KCl is dissolved in 1 kilogram of water, the boiling point is raised by 104 K. If the degree of dissociation is overlooked, it may seem that the mass of 2 moles of particles is 74.5 grams, leading to a miscalculation of the molar mass. This misunderstanding highlights the importance of recognizing how solute behavior impacts solution properties. In contrast, ethanoic acid molecules dimerize in benzene due to hydrogen bonding, which reduces the number of particles in the solution. If all ethanoic acid molecules associate, the calculated boiling point elevation will be half of the expected value, resulting in a molar mass that is twice the normal value. This phenomenon illustrates the complexity of molecular interactions and their effects on physical properties. To account for these variations, Van't Hoff introduced a factor known as the Van't Hoff factor. This factor, denoted as I, is defined as the normal molar mass divided by the abnormal molar mass. Understanding this factor is crucial for accurately interpreting experimental results in chemistry. When a solute dissociates, the value of I is greater than 1, as seen with KCl solutions, where I is close to 2. This indicates that the solute produces more particles in solution than initially expected. Conversely, for ethanoic acid in benzene, where association occurs, the value of I is nearly 0.5, reflecting the reduced number of particles due to dimerization. These concepts of osmosis, reverse osmosis, and abnormal molar masses highlight the intricate relationships in chemistry. They showcase how water movement and solute behavior impact various processes in nature and industry. Understanding these principles can lead to advancements in water purification, food preservation, and even medical applications, benefiting society as a whole. As the world faces increasing challenges related to water scarcity and food safety, the importance of these scientific concepts cannot be overstated. By harnessing the power of osmosis and understanding molecular interactions, innovative solutions can be developed to address some of the most pressing issues of our time.